Hi, everyone, and thank you so much. Welcome to my audiovisual entrainment and dementia presentation, especially with an emphasis on cerebrospinal fluid pumping or pumping of the glymphatic system. And I thank you all so much for attending my webinar here. So let's get started. Here we go. Now, the whole glymphatic system was just discovered, not that long ago. A dozen years or so. This is 2016 when these guys posted this in Scientific American. And what they found is that at night when we fall asleep, if we're making large delta waves, there's a pumping action that occurs. And all the metabolites of brain function during the day and cognition during the day will get pumped out into the, there's a space around the vein. You can see the vein here, there's a space, it's full of cerebrospinal fluid. And it gets pumped into that. And then it gets dumped into the vein and carried out also through the ventricles and dumped into the lymphatic system. And so, and they really thought that astrocytes played a big role in removing the waste products during the day that built up during the day. I'm not sure that astrocytes are necessarily thought to be that now, and I'll show you why in a few minutes. But anyway, because they figured it was an astrocytic lymphatic system, and astrocytes are part of the glia, they called it glia lymphatic or glymphatic system. And they're finding that glymphatic problems are rampant in chronic traumatic encephalopathy, Parkinson's, and Alzheimer's. And this might be the biggest deal, as to why these conditions happen. And unfortunately, we don't have very much research, but we have enough to make a case. So here's some things that affect the glymphatic system. Upregulating factors, exercise. And if you're exercising, you've got blood flow happening all over. That's going to cause cerebrospinal fluid to be exchanged and circulated. Sleep, which they're showing non-REM or big delta waves, complex type sleep. Lifestyle choices, good food and everything else. All are factors that improve glymphatic flow. Things that reduce it are blood-brain barrier altered permeability, neuroinflammation, which so many people have nowadays. And that's the primary thing with Alzheimer's, post-concussion syndrome, Parkinson's, is there's neuroinflammation. Probably quite high also in diabetes and things like this. This AQP4 polymorphism, and that is a protein that helps to dump or circulate fluids, water. And it's an issue if it's not working right. In aging, there's issues with aging too. And aging might not just be getting older, but as we age too, we have a tendency to get more sedentary physically and stuff like this. So that could also be just a part of the problem that our lifestyle activities change some and we tune them down as we age. Now, this is a little study done, and this is interesting here. What they showed is that they're looking at the internal carotid artery, the internal jugular vein, and when there's a pumping action occurring, as you can see up top here, a little bit later, it takes a moment when the heart beats for that pulse to show up in the brain as intracranial, as increased blood flow and intracranial pressure, and then the spinal fluid gets moved. It has to balance out the intracranial pressure, so there's an outflow of cerebrospinal fluid. And then a moment later, you see the cerebral blood flow change at the internal jugular vein. So this whole process takes a little bit of time. Every time there's like a heartbeat, there's a little bit of exchange of cerebrospinal fluid. It's not big, but it happens. So, and then this group here took it one step further. They were using mice, mind you, but mice, being the smart little creatures that they are, done a lot of good things with mice. So they're looking at daytime levels of norepinephrine in the brain, right, in locus coeruleus. And it's just, kind of randomly going up and down as the mouse is doing things. And these changes in norepinephrine do cause slight changes in arterial volume or arterial size, diameter. But at night, when the mouse is asleep in non-REM sleep, so deep delta sleep, And they get these pulses of norepinephrine, which cause a real pumping action. So I'll just do over this slide one more time here. So what they found with mice is that mice during the day are making, there's changes in norepinephrine as the mouse goes about its daily activities. It causes mild pumping actions in arteries. And here's the perivascular space where the cerebrospinal fluid gets exchanged into the arteries to be dumped into the lymph system later. But at nighttime, when the mouse is making non-REM or large delta wave sleep, there's a big pumping action that goes on the arteries. And they have found a couple of things. One is this pumping action can pump cerebrospinal fluid into the brain, and it also pumps it out of the brain. So it has a circulation pattern that goes on. And that wasn't, I don't think that was known in the original research way back, but it's known now. And what's really interesting is look at this here. Ambien, the sleeping pill Ambien, suppresses norepinephrine oscillations and lymphatic flow, and it's now being linked with dementia. So not good to use Ambien. Now, I don't know if, so far, I haven't found any research on other sleep aids, but if that's supposing they're all interfering with norepinephrine, then sleeping pills are definitely dangerous in the long haul, for sure. But Ambien has been found out so far. Okay, we'll go on to the next slide. So this is traumatic TBI and Alzheimer's disease. Now, I've always said that TBI, or chronic traumatic encephalopathy, and Alzheimer's are the same thing. Everything I've been looking at over the last 10 or 15 years tells me they are the same thing. And these guys finally said it in their study, so I was kind of pleased about that. So here they're showing the TBI at the top here, right there, and beta amyloid accumulation. Of course, there's sleep interruptions that start to happen following the brain injury, and there's inflammation. And inflammation is pretty key because I've got so many people with neuroinflammation, and it all leads to dementia, it seems, but it's quite treatable. Anyway, they get cerebral vascular damage and clearance impairments. And it may not be necessarily so much damage. These guys call it damage, but it could just be impaired functionality, which isn't necessarily damage. I think we're seeing impaired functionality more than we are seeing damage. Anyway, there's contributing factors that will add to this. Again, diabetes and other things can be certainly inflammatory. There's increased beta and tau accumulation, beta amyloid. Perivascular damage again is what they're surmising. Increased cerebral vascular damage, and they cycle through to cognitive impairments that are Alzheimer's-like. And I'm saying that they kind of are Alzheimer's, and I think they're the same thing. So deep sleep deprivation, this is really important, and there's quite a few studies on sleep deprivation showing that if you don't sleep well, you end up with Parkinson's and CTE and Alzheimer's. And all these people suffered from poor sleep for years. And if you have poor sleep, you're not going to get the pumping of the glymphatic system. And there's just more research on this showing this study here. They were showing here that human and animal studies have found impaired sleep preceding cognitive problems in patients with Alzheimer's, and so on, and so on and so on. You can read all that. I don't think I need to read it to you. But they've also noticed that the norepinephrine in the cortex from the locus coeruleus plays a factor in Alzheimer's, which they kind of knew before the glymphatic system was discovered. So this is a very fascinating study in itself. And here they looked at 2,442 subjects. They were married couples, so 1,200 married couples. And one of them had dementia. And so if one of them had dementia and the other, and was getting up, because people with dementia will get up at night, they'll do weird things. Maybe they'll light a campfire in the living room. You don't know what they might do, or leave taps on, or walk out the front door. So the caregivers, the other spouse, is often up at night dealing with issues. And they had a 6-fold increase in the risk of dementia compared to those who are dementia-free. So that says a lot about sleep, even if there's no medical, contributing factors to it. If there's a lifestyle contributing factor to it, your risk of dementia increases. Now, studies on the E4LL, I thought, well, this will be interesting, looking at that gene problem, how it plays out in Alzheimer's. I was trying to find an angle here, how it played out. And guess what? The primary symptom of the E4LL is sleep impairments. Well, that might be why it is tied to Alzheimer's. Now, this is a really nice little study. I was trying to find something like this with Alzheimer's, PTE, and I just couldn't find good graphic representation like I did with this one. This is Parkinson's. And here, what they're looking at, these are controls on this panel here. And they're showing these red spots are showing cerebrospinal fluid circulation, so movement. And they found that those with Parkinson's had much less movement in the fourth ventricle than the controls did. And that was one of the findings. Okay, so now we're going to talk a little bit about entrainment.
Laura's asked the increased risk of dementia with spouse dementia due to mirror neurons.
I don't know about mirror neurons per se. I mean, normally mirror neurons are a factor with autism spectrum disorder, but I don't know. Did it say that there are mirror neuron issues in that slide? I didn't think there were. I'll go back to that. Here we go. Yeah, okay. No, I don't think there's anything to do with mirror neurons. I think it's entirely just the fact that they're not making large delta waves and they're not getting any pumping of cerebrospinal fluid. I'd have to maybe talk later after we're done and see what her where she's coming from with that suggestion. So, when you do neurofeedback, and I've always had an issue with this, when you do neurofeedback and you see someone has too much theta or not enough theta, or too much beta or something is off, right? Not on the norm. The first thing we should do, I think, instead of trying to tune those frequencies up or down, we should say, well, why are they there? What's the underlying physiology that's causing these frequencies to show up in the brain? Let's address that first. I mean, I have so many clients with brain issues because they were deficient in vitamin D. I went through some serious difficult stuff when I was deficient in vitamin D. I can tell you, and my brain was a wreck. B vitamins, same idea. Really need good B vitamins. You need all our vitamins, and honestly, Ron Swatzina looked at a group of kids in primary school and found the ones that were eating, the Captain Crunch and the stuff like this, the rotten breakfast cereals. By 10 a.m., they all showed high theta because they would have had a crash in blood sugar, right? And so they all had high theta and ADHD-ish like behaviors. If you put them on a meal of ham and eggs, peanut butter, tuna, something with good protein and slow release carbs, they were functionally perfectly fine, and the theta was quite down in the EEGs. So some of the things about entrainment that is wild, and of course, when entrainment first came out, it was all on a frequency model. That's all they knew. You flash lights in the eyes or sounds in the ears, and you could bring the EEG up or down, at least in the moment. But entrainment doesn't. I mean, we're all alive here. We don't want to be wearing machines all day long, 16 hours a day while we're going around our lives. We want to do a session just like you would with your feedback for 40 minutes or 30 minutes, and then go about your day, and hopefully you'll be functioning better throughout the day. When you look at all these things, especially when you get into the physiological parts of it, breaking the HPA axis, increasing cerebral blood flow, lactate anaerobic ATP, or neurotransmitter productions, or exciting the glia, or increasing heat shock protein, or activating specific non-inflammatory cytokines, which was Singer's work using gamma. Direct effects on neurostimulation, which was John LeMay's P300 work. He found it has had a stronger P300 and the latencies were a lot tighter. And now we've got increased cerebral blood flow circulation is the latest discovery that we've made. And all of these use frequencies that have nothing to do with what you would do in neurofeedback. And some of them are just broad. It just happens when you do entrainment at any frequency, and some are more specific. Either which way, if you did entrainment, like here's an example. I used to have lots of good conversations with Herschel Tumim, and he was doing his little hemoencephalograph, and he was teaching people to increase their cerebral blood flow, like kids with ADHD and so on. And we had several discussions, and we knew that entrainment increased cerebral blood flow, and we put a person on his HEG and saw pretty remarkable differences. And then just like a week or two later, I got home, and a couple weeks later, I got home from the ISNR conference. A couple weeks later, I get a girl, a college student. She's dropping out. She's in such a state of fog, she can only read 2 paragraphs, and then she's fogged out. She is 4 standard deviations high at about 8 hertz. Well, the research by Fox and Rakeley showed that entrainment, like visual stimulation, across the board increases cerebral blood flow quite a bit, and it also increased oxygen consumption, whole brain oxygen consumption, not just in the visual cortex, but everywhere. And it peaked at 8 hertz. So this girl is high at 8 hertz already. So from a frequency model, I'm going to give her exactly what she should not have. I should be giving her beta or something like this, and you know, with neurofeedback, you do an inhibit on that 8 hertz. But I gave her exactly what she should not have on a frequency model, but I gave her exactly what she should have on a cerebral blood flow model. And cerebral blood flow certainly affects all those slow wave activity. So I gave her 8 hertz on the machine, on our device, and for about, I don't know, 25, 30 minutes. Take a 15, 20-minute break because there's a recovery period that Tom Budzinski showed us years back. And then I did the EEG, and she was now half a standard deviation off the norm, as opposed to 4. And now I had her read 10 pages, and she was cognitive on all 10 pages. I asked her questions about what she had read, and she could answer them. So that's an example of giving someone exactly what they should not have on one model, but it's exactly what they should have on another model. And so you can't think of entrainment from a frequency model. It kind of works some, but often does not. So hope that helps. Now we're going to talk about a thalamocortical disconnect, which I've been working with for at least 10 years now. The EEG is low voltage fast in some channels or all channels. And I'm going to show you a guy who is just flatlined. Oh, just flatlined. They normally have theta down the midline. It's still low voltage theta through the cingulate area, but it's still higher than all the other activity that they're making. And they have severe phase issues. Now, I still use the skill database for this because it is still, I find, the very best measure or system to measure phase issues. And we mostly see them in the beta bands. I think this has something to do with the fact that there might be less, the oligodendrocytes are quitting myelinating. And so we're seeing slowing in sections of the brain that are affected. There's a fair bit of research on that. And basically, if you shut down, let's say 50 billion neurons from making an alpha wave, and there's 4 synapses to complete the loop between the cortex, the thalamus, and back to the cortex, you're going to lose 1 trillion. If you lose your alpha, you're going to lose 1 trillion action potentials every second. And if you do, and the oligodendrocytes must see action potentials to know where to myelinate, I mean, you're just hooked. What are you going to do, right? The brain is going to start to come apart. So anyway, I'm going to show you this guy here. I've got lots of these, but this guy was very interesting. He was one of my toughest, the worst cases I had seen. And on intake, he had completely forgotten he had a fall. He didn't even remember it. And then I did the EEG, and I said, holy smokes. I said, you have had a big concussion here sometime. And he goes, oh yeah, I forgot when I was 6, I fell off the slide and I punctured an inch deep hole in his skull. Well, it says left skull. It was actually on the right-hand side. So anyway, yeah. And this guy, it shut down all his alpha production. He couldn't sleep. He couldn't function. He was in a fog all the time. Can't socialize if you're in a fog all the time. He and all these people become obsessive compulsive. They're hoarders, counters, cutters, ritualists, door closers, knockers, tappers, anorexics, every single one, pretty much. Or they're just very obsessive about things being perfect in the cupboards, like all the plates and stuff and cups arranged perfectly or something, but they're typically obsessive about something. And sometimes it's pretty severe. It's clearly clinical. And they all have the same, pretty much the same pattern. So this guy lost his license from a DUI in 2013. Then he was in rehab. And then he snuck in alcohol and was kicked out of rehab. Then he spent days in detox. And he lived in a friend's basement suite for really cheap rent. And he did odd jobs like helping people move furniture or move their homes, and he made enough money to buy some food and alcohol and get really drunk again. He was self-medicating, and when you talk to people who knew him, oh, they said, oh yeah, he's a deadbeat, he's a useless, he's a waste of skin, all these terrible things people said about him. And it wasn't his fault. And here's his EEG. Now, my room is set up to make alpha waves. I'm very careful on how I do this when I do a recording, because I'm looking for guys who cannot make alpha waves. And if the room is too bright or it's noisy or the chair's uncomfortable, they won't make alpha waves. So I have a nice reclining chair. I have a footstool. I put their legs on the footstool. I give them a light blanket. We put on a fan for white noise. Dim all the lights so it's fairly dim in the room, and it's very conducive for alpha waves. Any person will make piles of them. This guy, for the life of him, could not make an alpha wave. And we tried, but we could not do it. So take a look at him. There's his alpha, gone, absolutely gone. And in frontal areas like along FZ, CZ, definitely FC in that area, the cingulate also goes through the caudate on its way to the thalamus, and so there's even more connections. And of course, the caudate is implicated Tourette's type symptoms and obsessive stuff too. So there's a few things that are added in those areas of the brain. So remembering again about the cerebrospinal fluid circulation that we want to increase here unwittingly. So we put them on entrainment. Now, these guys don't make alpha. This is another one of these counterintuitive things. You cannot use the frequency model. I give all my guys for years. I gave them alpha, working on the frequency model that alpha would hopefully increase their alpha, and it mostly never did. And I was always kind of stumped. I wasn't able to help these guys. And then I came across an ultrasound study where they actually used speakers mounted above the ears, and they pounded the thalamus, and they could excite a thalamus using ultrasonic pulses, but they were done in the beta band. And then I came, and that was the band that worked. And then I looked at another study where they used needle electrodes implanted into the thalamus. And again, they were using beta frequencies like 20 hertz and up. And so I'm like, okay, well, then let's try that. So I had my first client that I tried that on was a girl who was anorexic. And she became anorexic after a severe flu. And that neuroinflammation interfered with maybe her cerebrospinal fluid is what we're guessing. And she became anorexic. And she was pretty flatlined, and we had massive alpha spindles happening pretty quickly with her. But this is this guy here. Now, this guy, I'm giving him, in this case, an alpha beta blend because he had depression. So this is our mood booster protocol, but it's very complex stimulation. You got 10 hertz in the left fields, you got 20 hertz in the right fields, and we randomize it. So it's bouncing around some. And 15 minutes in, he starts pounding out a whole bunch of alpha. And as he fell asleep, because these guys are sleep deprived, alpha spindles were mixing in with delta, big delta K complex waves at the same time. And he was starting to make delta here, and then you can see it here on the picture, and then waves of alpha. Now, what's interesting is about half of my clients, when they first make this alpha, it runs fast. It's 12 hertz, 13 hertz. It settles down over a few weeks and slows down to 10. But it starts off very fast. It's like a norepinephrine thing is happening. I can't quite explain it, but it does have. So if you see it, if you do this and you see them running fast, don't worry about it. It will happen. So here he is right after, and you can see that his alpha has been reestablished. So very, very nice. Here's his OCD a little bit showing up here still. but largely it's been reestablished. So he slept for 30 minutes after entrainment ended, and then he slept 11 hours that night. He continued sleeping well. He had reduced anxiety. He had no cravings when I saw him 9 days later. Still no cravings for alcohol. And I saw him in the fall. I think it was October of 2017, I believe, maybe 18. I think it was 17. And anyway, he pretty much quit. Well, yeah. Anyway, he quit binging entirely. He was drinking socially some, but he decided he should probably stop drinking entirely. And now that his brain was stable and he was making alpha waves again, he stopped drinking entirely in January of 2017. Now he's a heavy equipment operator. Before he couldn't hold the job, and he has a girlfriend. They're getting engaged, or they were engaged as a year ago, and so big changes. So I saw him 3 years later, and we ran an EEG on him to see if, I mean, clearly his life had changed. So we should see that change show up in the EEG. And here it is. So we went from a guy completely flatlined, eyes closed, to a guy making beautiful alpha spindles, eyes closed. So we fired up his brain and away it went. And he's been good ever since. In fact, he's been really good. I'll show you in a moment. So here he is, this is 2.3 microvolts here. And here we're looking at 2.5 because he was making so much activity here. And you can see here is, after entrainment, he was up here, but for whatever reason, this day he was a little slower. But nonetheless, he is very functional now. And he was very proud of himself. This was 5 years sober. Certainly back in, I don't know, 2021 or so, he was 5 years sober. Very, very, very proud of himself. And so he should be. So now we're going to talk about the cerebrospinal fluid induced by sensory stimulation. It's a study done by Williams in 2023. I came across it last year, and they were just doing a proof of concept study. That was it. And they didn't have any clinical attachment to it or implications from it at all. But I connected the dots really quickly. The two experiments, they're looking at neural, hemodynamic, and cerebrospinal fluid signals during visual stimulation using EEG and fMRI at high temporal resolution. And then they did other experiments too, partly to replicate the findings in experiment 1. Show some of the pretty pictures. So here they go. They have a visual stimuli here, which they are flashing at different frequencies, 4, 8, 12, 20, 40, for different periods of time. Now, in this example, they're doing 16 seconds on and 16 seconds off. That was the most optimal time for the most optimal exchange of cerebrospinal fluid, was 16 on and 16 off. And I use 15 on and 15 off. It seems to be working fine. And then they were measuring the cerebrospinal fluid right down in here, going in and out through the fourth ventricle. So now here they're looking at, in panel C here, they're looking at all the cortical activation when the lights are being stimulated at high speed here. And they're showing, now down here, they're measuring cerebrospinal fluid right here. And they're showing how it's changing when the stimulation is on. There's a pumping out. And when it shuts off, there's a pumping in. And so when it's on and you have all this cortical activation, well, now the cerebral volume and all the arteries is larger. So the brain has to maintain intracranial pressure. So it's going to dump the cerebrospinal fluid. And then when you shut it off, there's an absence of, or a reduction in intracranial pressure. So it has to bring it in. And so we can see that after they shut off the stimulation, very shortly after, the brain is bringing in cerebrospinal fluid through the fourth ventricle. Experiment number 2, they looked at a couple of different places, but largely it was the same idea. The stimulation is on and there's an outflow of cerebrospinal fluid. They bring it off and there's an influx of spinal fluid, turn it on and that goes out again. And that's basically what they were doing. Now, for those of you who want to watch this later, there you go. This explains all those little pictures. I'll just leave this up on the screen for about 10 seconds. And then when you watch the video, you can pause it, you can rate it, and then you can go back to the pictures, right? So here we go. Okay, so I'll move on. They did another study, and this is same. Sorry, not another study. This is the same study, but different things they looked at in the same study. So here they were looking at the blood oxygen level dependent measures across different stimulation durations. Now here they're looking at 0.2, 0.5, 1, and 4. They actually found that 16 seconds was the very best. And you'll see that 16 seconds on, 16 seconds off. And so they're looking at the different signals in here. Now they're looking at spinal fluid flow across stimulus durations. Again, 0.2, half, 1, and 2, and 4 seconds. You can see here, as there's that stimulation period, 4 seconds on, 4 seconds off, gets longer. The cerebral spinal fluid exchange gets better and better. And it actually is best at 15. And here they actually were playing around with this. And these are different frequencies here at 15. And so 15 on, 15 off, because they determined that was the optimal time frame. Well, actually, it was 16 was the optimal time frame. So they tried different frequencies, and you can see the different frequencies. They had some impact on the exchange of cerebral spinal fluid. They determined, if you look at these, that 40, 12, and 8 were better than 4, although 4 was still pretty darn good, but they were a little bit better than 4. And same thing with the blood flow here, again, or spinal fluid flow across. This is the blood flow, and this is the spinal fluid, and you can see how it correlates when they're off and the blood flow is crashing, or the spinal fluid is coming in. When the arteries are all dilating like mad from the stimulation, spinal fluid is going out. So just that simple a process. And who knew? So anyway, here you go. This explains that last slide, and I'll just leave this up for a few seconds, have a little sip of tea, and then we will move on. Okay. So as I already explained, yeah, these changes were made. There's a big difference between there definitely was a big correlation between the global bold signals of cerebral blood flow with the cerebral spinal fluid changes and so on. And the 16-second on and 16-second off were the optimal time periods for maximum exchange, because it took about that much time for the cerebral arteries to expand and build up pressure under the cranium, and then for the brain to dump the cerebral spinal fluid. After 16 seconds, there really wasn't much change because everything had changed state and the arteries were already large, and so it became sort of static. And if it was too short, there wasn't enough change yet. So 16 seconds on and 16 seconds off, they determined, was the maximal exchange. And they could exchange 10% on every cycle. So we're using 15 seconds because I could fit that into a minute when I was programming my gear. But that would, and we're also adding audio stimulation, not just visual, but we're adding audio as well. And so that would, give about a good 20, I don't know how much more the audio is going to add to the visual, but I would expect we're seeing all of 20% exchange in cerebral spinal fluid per minute. So it's a lot. And so anyway, EEG of photic driving showed a clear temporal sequence of events, which we already talked about, the stimulus duration, which I talked about, the cerebral spinal flow or fluid flow is coupled to the systemic physiology, and it's in parallel to the neurally driven flow, which we know. And yes, and here we go. And so the visual stimulation here induces significant response in 9% of the voxels across the entire cortical gray matter, confirming that high intensity stimuli effectively drives large hemodynamic changes. Yeah.
I understand that training SMR 12 to 15 hertz over the central strip increases the thalamocortical loop. You just mentioned alpha and data in connection to this loop. Could you briefly comment on SMR?
I know people who have, I guess you're talking about neurofeedback training. They have tried everything, including SMR, and some people have done 50, 60 sessions on people with this signature, and they have had no changes. And this is how they got onto entrainment, because they were giving up. And it kind of makes sense that you wouldn't, because it's not a frequency model that's causing this problem. I like to, this is my analogy. I like to compare neurofeedback to a light dimmer. Supposing you've got a light dimmer, you've got a light on the ceiling, there's a light dimmer, and you can modulate the brightness of your light by tuning up and down the light dimmer. And neurofeedback gives you the ability to do that and modulate how bright you want that light to be, till it's at an optimum brightness. In this case, though, you've really got a break in the wiring somewheres, and you can turn the light dimmer all you want. It's not going to make the light get brighter or dimmer at all, because there's a break in the wiring. So you have to fix the break in the wiring before you can modulate the light dimmer. And that's my analogy for it. But no, I've talked to quite a few people, because I've been really active in this for quite some time. And neurofeedback, they have not seen it work at all. Now, I will say, though, once you boot up the brain and you start getting alpha waves and such, you can then go in and use neurofeedback to fine tune the system. And that's certainly fine, but you need to get the system booted up first before you can proceed with other interventions, is what I believe anyway. Anyway, so we'll move on. So this is Sherlyn Budzinski, Leslie Sherlyn, which you guys probably all know, and Tom Budzinski, who's since passed away. This is 2002. And they were using a system of hours that could do 10 people at a time, and they're using it in 2 seniors' homes. And sort of by accident, they got this lady who was 57 years old, and she had rapidly progressing Alzheimer's. And she wasn't expected to live long. So Tom had me develop a pseudo-random entrainment session that was about 30 minutes long, ranging from 9 to 22 hertz. It had all of 100 modules, maybe 110 modules in it. But not only did he bounce the frequencies all over the place, he also bounced the intensity of the lights. Sometimes he would make it bright, and then other times dim. And sometimes he would make those changes in 5 seconds, and sometimes 10 seconds, sometimes 15 seconds, or even 20 seconds, making it bright and dim and loud and quiet as well. So just by sheer dumb luck, he was pumping cerebral spinal fluid, and none of us knew it at all. I mean, and it wasn't until I worked with this Alzheimer's girl using the SMR beta, and I got her completely functional, and she completely quit being not Alzheimer's. So the girl that I was working with who had the anorexia, that's what I meant to say. And we got her completely cured of her anorexia, and she went on to have a normal life and put on weight and so on. So that's when I thought, okay, I got to take a look here and see what we were doing with that Alzheimer's thing. So I bugged Leslie, and of course they hadn't. That data was long shelved away for 15 years or so. But he did find it for me, and we pulled it up, and sure enough, there were some things that were very interesting, which I'm going to show you right now. So they did QEEG, and they did Loretta's at baseline, so pre-stimulation. After 30 sessions of entrainment at 12 weeks, and that's what we're going to call Q2. Now, after Q2, she was well enough to go home, and she didn't need to be in the senior's home anymore. But she did show up for maintenance treatments, randomly, kind of like every once in a while, occasionally, for that period from 12 weeks to 6 months. And that's Q3. And then after that, she did nothing at all. And that's 10 months. But once you get that brain booted up, the improvements seem to continue to happen. And we've noticed this in a lot of people that we've worked with. So she used it intermittently during Q2 and 3, as I said, and she stopped using it between Q3 and Q4. So they noticed that during stimulation, that the delta at T4 primarily went down. She had high delta. And it was down more again after 30 sessions. In fact, the whole brain started showing dramatic decreases in delta. And so here's what we see here. So this is Q2, and the blue means it went down from baseline. And you can see it's not just the right temporal areas, but mostly in the right temporal area. And then it starts getting more into the left as well as the right. This is at the at Q3. At Q4, we see the delta is down quite broadly, you know, and across both temporal lobes, and so on. So and she had no stimulation between this one and this one. So her brain is just booting itself up. Now this is the piece de resistance. At baseline, she had no alpha, but nobody knew what that meant. So they just observed it. After treatment, she had a big alpha rhythm right there. And so that is the important part of what's going on here. And when that alpha went up, you can see also delta and stuff are coming down, as we saw in the pictures. So this is what they observed. They called it audiovisual stimulation, and that's okay because they weren't really using entrainment so much. I mean, you can entrain in 10 seconds, and they were often running, 5 to 30 seconds or something on their different frequencies. But audiovisual stimulation is probably a bit of a more correct way of saying it. And since this time, we have been experimenting with mild randomization. In fact, all of our stuff now is mildly randomized. Not too much. If you randomize too much, it doesn't work. But if you randomize it just a small amount, we've been experimenting with this for 20 years and actually have a patent on the randomized AVE, which we call RAVE. But part of that was what we saw with Tom's study, where he wasn't really using entrainment, but had remarkable improvements. I mean, how do you just reverse somebody with rapidly progressing Alzheimer's and make it completely normal so they could move home? Anyway, she was able to walk, accurately find her way around a several block radius, including the distance from her home to the site of the training at the senior's home, before she was lost in the senior's home. Her walking style improved from the shuffling, flat-footed stride of many Alzheimer's patients to a more normal gait. She reported that the cognitive fog lifted after her training. The microcog calculations showed that her reasoning and such improved. And so entrainment appears to produce improvement in the current density, meaning the Loretta, of various brain regions that are involved in Alzheimer's disease progression. The results appear as early as the first entrainment session and last through continuation of the 30-session training period. That was their conclusion. We could really use people who want to do some clinical work here and report back to us and tell us how it's working. So anyway, that is the lecture part. So thank you so much for listening. I appreciate it. Well, I should mention Becky Basham has got lots of data on football players who were making $1 million salaries and ended up living in the streets, some of them. And I see Becky's here. Hi, Becky. And she can tell you some stuff too. And so is John LeMay. In fact, Becky and John LeMay, I have made them our scientific advisors for Mind Alive because they're so good at what they do. And they have so much knowledge and experience. So hi, Becky. It's good to see you.
Well, it's great to be here. Really appreciate all of your work, Dave. It's been instrumental in helping me to serve my population.
Thank you. Now, what we've done with the actual pumping session, so I didn't get the pumping session built because I couldn't do it on the old machines. And we just got this premiere ready in November. And it was about December 15th when I got these pumping sessions in place. And I made 3, one at gamma at 40, the other one at 12, the other one at 8. I don't like the gamma one because it sounds like you're in a factory. It sounds like when it's pumping at 40. It's not a pleasant sound for me. However, a year ago, I had a very, very bad cold. It came out negative as COVID on the home test, but it might have been COVID because I lost all my smell entirely. Couldn't smell a thing. And after 2 sessions of the gamma, I had a fair bit of smell back. But I didn't like the gamma, so then I went down to the 12 hertz one, which I do quite like. And I've done a good 30 sessions now, and I've got all my smell back entirely. And I've discovered that there's good smells, and there's some smells that aren't so pleasant. And sometimes I make them. But I can smell again, so I'm pretty happy about that. And a loss of smell is one of the first signs of Parkinson's. And Parkinson's patients will often lose their smell for 4 or 5 years before the other motor symptoms start to show up. Well, I've got a client right now with Parkinson's, and he's been using the SMR beta protocol for about a year now. And he went from not being able to type. He was too shaky to type, and he was too shaky to handwrite. And now he can type, now he can write. So his improvements have been reasonably good using the SMR beta, but his smell never returned. So about a month ago, I got him on the pumping protocol. And he reported last week that he could smell dinner for the first time in 10 years. So there's something to it. Anyway, I just thought I'd share that with you. And sure, so anyone wants to add anything, I'm going to fire up a session right now as well. Now,
So there's a question to this one.
Oh,
Is
yeah,
it
sure.
is it possible that the pumping sessions in David Premier will improve the symptoms of insomnia? Then what is the mechanism to explain the pumping effect of visual stimulation? Are there similar studies showing pumping effect from rhythmic tactile stimulation vibrations?
I don't know about tactile. I've not seen it. We based this on that Williams study that was done in 2023 that I showed you just now.
So there was 3 questions. Is it possible that the pumping sessions in Premier will improve the symptoms of insomnia?
You know, I think so, yes, because so much, the research is coming and they're finding that when you start having buildup of proteins in the brain, you're going to have insomnia. The brain is just really unhappy about it. And you will not sleep well at all. Now, lack of sleep seems to cause it to some degree, but the inflammation, so there's a bit of a chicken and egg thing seeming to go on here. The inflammation from a viral infection or from concussion starts to cause problems, as we saw in one of the earlier slides, with the whole system of exchanging cerebral spinal fluid. And right in around the same time, insomnia starts to increase terribly, which further exacerbates the problem because now they're not making the delta waves needed to pump it. So how do you get them into making delta waves to pump it when they can't sleep in the first place? You're hooped. There's no way out of that. So if audiovisual stimulation will pump it, you can get it pumping. And theoretically, you should be able to then really start dramatically improving sleep. Now, the research is still too new to actually know that. I know I use it myself. And I got to say, it's weird because it's on for 15 seconds. It's going to doing its thing. And then it shuts off for 15 seconds. Now, I have a heartbeat that plays. So it goes boom, 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 boom. I'll play this a little later. And you can add sounds to it because you need a little continuity in that off period, or it's kind of strange if you don't have some continuity. It's too dead. So on the Premier, we can add all kinds of sounds. You got babbling brook, ocean waves, pink noise, white noise, brown noise, birds, chimes. You can add all these sound effects to the session. I really like the babbling brook. So when it goes down, I hear this babbling brook and the heartbeat that plays, and it just keeps me connected for 15 seconds until the stimulation comes back on. But other than that, everything is dark, and I'm like, okay, well, this is boring. Then it comes back on. I go, okay, that's kind of nice. Then it shuts off. Okay, this is boring. And then I wake up a half an hour later. I don't know how I fall asleep, but it puts me to sleep every single time. And our Parkinson guy, he goes to sleep every single time too. Does everybody go to sleep? I don't know. No, sorry, Becky does not. She gets relaxed, but she does not go to sleep.
I also get focused. It gives me, I relax. It slows down my mind, but not in a foggy, groggy way. It slows my head down and helps me to feel more clear and focused. It's kind of like cleaning the windshield.
Well, a rapid, anxious head can be caused from slow brain function, right? Where it's not putting on the brakes, right?
And I feel like I have more energy, like I can keep going. I do it for an afternoon break often.
Yeah, I get the energy too. I get very good. I really need it sometimes to get good energy and get booted up again. Yes, absolutely. So here's the gear. This is it here. I'm going to hit this button here. It's going to power up. Now I've already been using this session, so it's in a category called frequently used sessions. Otherwise, you need to go into the library, the AVE library. If you go down here, that's the session library. There you go. I can go into the AVE section, and then I can scroll down, and I'll find it in the research category. Whoops, AVE sessions. There we go. So here's relaxation. There's a whole bunch of different protocols in there. This is relaxation, and it's in this section here. So I can go into this section called research, and I can dig through there. And I got a variety of different ones. Some of them that are not on the system. Some I've made for myself because I'm experimenting. But you can go through these research ones, and you'll find it in there, and you can then run it. Here it is. Here, the SMR pump right there. But it's in my because I use it, it automatically stores it into a recently used category, so you can find it really fast. So I just hit the check mark there, and there it is. Bingo, it's ready to go. I'll turn it on, and it's going to start to run. And the eye sets are starting to go right here. You can see them going. Now, these Spectrum eye sets, I should mention, they're really advanced, and you can plug them into the USB port on your computer. And we have two sessions, one called Breathe, which we use for heart rate variability, which works really well. And another one called Live. I'm not crazy about the name Live, but you can run it manually. But you can also build sessions on our editor, drop them into your computer, and you can play this straight off the computer. And the computer will make all the sounds, the bup, 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 bup sounds. You can put the babbling brook in there, the other sound effects. And you can work with clients straight off your computer with this session and the Live app, which is free, and then you can even record your session, and it'll build the protocols for you in live, in a live, like in real time, and then you can download that into your device. Another thing about the device that's really fast, interesting, or really good, it's a big improvement. You can see there's an SD card. So all the sessions are stored on that SD card. So when you get your device, I recommend you take that little SD card out, plug it into your computer, and download all the sessions onto your computer and put them in a file folder. Then you can say, if you want to use our Live app on the computer and plug into the computer instead of use the device, you can download all those sessions into the computer, and you can run them straight off the computer. So it's pretty flexible. We can do with this iSet. So now it's turned off. I'm going to turn on the sounds too, so you get an idea of what it sounds like. Anyway, that's how the process works. And that's the one at 12 hertz. I say the one at gamma is a bit of a kind of a sound. I don't care for it a whole lot, but it still works. Okay, I'll just turn that off.
How or why would one choose one of these CSF sessions over the other? So what would make you decide which one to choose? And how does someone determine which frequency is most appropriate for their desired outcomes?
Well, they were all the same. I would say choose the session that you enjoy the most. I did not care for the gamma because I found it sounded too much like a machine. But the 12 hertz, I really enjoyed the 12 hertz. And the 10 hertz or the 8 hertz one that we've got in there is good enough too. But yeah, that's what I use. But anyway, you can design your own. Just if you buy a machine, take that little card, download everything, and if you get the editor, you can go into the editor and change the frequencies to whatever you like.
Oh, and then there was another one. Who would you not use this system with? So who would it contraindicate with?
I don't know if it does. I typically don't see entrainment for all the years I've done it. I generally don't see it contraindicated at all. Not the way we do it anyway. You know, in the old days when people used high intensity square waves, entrainment at least was contraindicated with people who had seizure disorders. But once we started rounding the waves into more a sine-like wave, so it doesn't turn on as quick, and started randomizing it mildly so there's no fixed frequency, which we found worked better clinically anyway. I just don't, we've now put quite a few people on with seizure disorders and they've had good responses. So, and maybe the seizures are also part of cerebrospinal fluid buildup and such too. You know, it's very possible. And the neurons are now, you know, losing their stability. Either which way, yeah, I don't really see a population or cohort that is contraindicated to use this.
If somebody's using the CES, if they have a pacemaker, they cannot use CES, the cranial electrostimulation.
No. And if you're doing with this in EEG, don't use the CES, or that's all you'll see on your EEG. Well, then I guess we can wrap it up.